Section: Introduction. In this section, we explore large language models, LLMs, that are trained on vast datasets from the Internet, which allows them to perform various tasks like translating languages, summarizing text, and answering questions. This success has sparked a debate about whether their abilities stem from simple operations on memorized data or if they indicate true intelligence. True intelligence would mean that LLMs have learned the underlying factors that generate the data. Recent evidence shows that LLMs capture concepts like sentiment and writing style, which are understandable to humans. However, many still view LLMs as systems that merely memorize information, questioning their intelligence due to the simplicity of predicting the next word. Critics argue that this basic method cannot explain the advanced capabilities of AI or the foundation for artificial general intelligence, AGI. We investigate whether LLMs can understand human-interpretable concepts despite relying on next word prediction, challenging the idea that their success is just memorization. Studies suggest that LLM representations do capture these concepts. To analyze how LLMs learn this through next word prediction, we introduce a latent variable model. In this model, we treat latent concepts as variables linked by causal relationships that lead to observable outcomes, reflecting the generative process behind concepts and observations. While previous efforts have modeled concepts as continuous vectors, we aim for a model that flexibly captures the data generation process. We represent all variables, both latent and observed, as discrete, which aligns with the nature of language and human understandable representations. We do not require a strict one-to-one mapping from latent to observed variables, as real-world data often involves complex relationships. Using this model, we develop a framework to evaluate if next word prediction can learn interpretable concepts. Our analysis shows that, under certain conditions, the representations learned through next word prediction closely relate to a linear transformation of the logarithm of the posterior distribution of latent variables based on input tokens. This connection provides insights into how LLMs might model aspects of human intelligence. Our analysis supports the idea that concepts in LLMs are often linearly represented. Our main contributions include introducing a new latent variable model to formalize language data generation with human understandable concepts, presenting an analysis that shows how LLM representations approximate a linear transformation of latent concepts, and providing experimental results that align with our findings across various model families. The equivalence of LLM representations to a causal model of observed data suggests that next word prediction can lead to a deeper understanding of the data. While whether this constitutes intelligence is debatable, it is certainly more aligned with intelligence than mere data manipulation. We present our latent variable model designed to capture the text data generation process. In this model, latent variables represent human understandable concepts, while observed variables represent words. We differentiate between input and output tokens in the next word prediction framework. Although modeling latent concepts as variables may seem at odds with the idea that they are linearly encoded, we will show that this approach aligns with and supports the linear representation hypothesis. Our goal is to create a flexible model that realistically approximates real language data without imposing a specific structure on the relationships between latent variables. Section Summary. In this section, we explore the capabilities of large language models, LLMs, to learn human-interpretable concepts through next token prediction, challenging the view that their success is merely due to memorization. We introduce a novel latent variable model that captures the generative process of language data, demonstrating that LLM representations can approximate a linear transformation of latent variables, thus providing theoretical support for the linear representation hypothesis. Section: Identifiability Analysis for Latent Concepts. In this section, we focus on the identifiability analysis of our proposed latent variable model. Specifically, we investigate whether we can uniquely recover the latent variables from the observed data based on our model assumptions. We conduct this analysis within the next token prediction framework, which is a common and effective approach for training large language models, LLMs. Next, we introduce the concept of next token prediction, which aims to learn a model that predicts the probability distribution of the next token, given a context or input text. This is done by applying a softmax function to the outputs from the model's final layer, similar to multinomial logistic regression. The model tries to approximate the true distribution of the next token by minimizing the cross-entropy loss. With enough training data and a suitable model architecture, we expect the model's predictions to align with the true distribution of tokens. We denote a specific observed token as y prime. The function that maps our input to a representation space is f sub x of x, while f sub y of y represents the weights in the final layer. We will demonstrate how these representations relate to the true posterior distribution of the latent variables in our model. By applying Bayes' rule, we can express the true posteriors of the latent variables given the input. Assuming our representation extractor has universal approximation capabilities and that we have infinite data, the next token prediction will converge to the optimal classifier. This leads to an equality between the posterior and the true posterior. Taking the logarithm of both sides gives us a connection between the inference model and the generative model. The left side involves a matrix vector multiplication, while the right side includes a logarithm of a sum over latent variables. To make this more comparable, we approximate the right side to resemble a matrix vector multiplication. If we assume that the mapping from the latent space to the observed variables becomes nearly invertible, our approximation tightens. We will discuss this in more detail later. Next, we analyze how tight our approximation is. This tightness stems from the invertibility of the mapping from latent to observed space. However, since this mapping is complex and not well defined in real applications, we cannot impose strict constraints on it, making it difficult to provide a solid bound for our approximation. We can gain insights into the tightness of our approximation by examining the transition between the two equations we discussed. This transition relies on Jensen's inequality applied to the concave logarithm function. For those interested in the bounds of Jensen's inequality, we recommend checking a specific section of our paper. When the mapping from latent variables to observed variables approaches invertibility, the conditional distribution of the latent variables becomes highly concentrated around a unique point. This means that for most values of the latent variable, the probability is nearly zero, except for one specific value, which dominates the distribution. Under this condition, both sides of our equation simplify to similar forms, ensuring a tight approximation. However, if the mapping deviates from invertibility, the conditional distribution becomes more uniform, spreading over a wider range of latent variable values. This reduces the effectiveness of the observed data in pinpointing the specific value of the latent variable, leading to a looser approximation. As the distribution approaches uniformity, we lose the ability to recover the exact value of the latent variable, making our approximation less accurate. In summary, the degree of invertibility significantly impacts our ability to recover latent variables, and we provide further empirical insights into this relationship in our figures. Section Summary. In this section, we analyze the identifiability of our latent variable model, focusing on whether latent variables can be uniquely recovered from observed data through next token prediction. We demonstrate that as the mapping from latent to observed space approaches invertibility, the conditional distribution of latent variables becomes concentrated, allowing for accurate recovery. However, deviations from invertibility lead to a more uniform distribution, diminishing our ability to pinpoint specific latent values. Section: Understanding and Unifying the Linear Representation Hypothesis. In this section, we demonstrate how the identifiability result from our theorem supports the linear representation hypothesis in large language models, LLMs. We begin by introducing the linear representation hypothesis and then explain how it can be understood and unified through the linear matrix A derived from our identifiability result. The linear representation hypothesis posits that concepts we can interpret as humans are represented in a linear manner within LLMs. This idea is backed by various empirical evidence, including 1. Concepts as directions. Each concept is represented as a direction defined by the differences in representations of pairs that only vary in one specific concept, like gender. For example, the difference between the representations of men and women is similar to that between king and queen. 2. Concept manipulability. Previous research has shown that we can change the value of a concept independently by using a specific steering vector. For instance, we can shift an output from false to true by adding a vector that comes from pairs differing only in the truthfulness of the concept. 3. Linear probing. We often measure the value of a concept using a linear probe. For example, the likelihood that the output language is French can be expressed in a logit linear way based on the input representation, where the linear weights represent the concept of English versus French. We also note that recent attempts to create a unified framework for understanding these linear properties have not fully addressed the reasons behind their emergence, mainly due to a lack of connection to latent generative models. While some research has tried to explain these properties through such models, it has two main limitations. It relies on strong assumptions about the mapping from latent to observed space, which can be too restrictive, and it mainly views the explanation through the implicit bias of gradient descent. In contrast, our approach does not impose such strong assumptions. Instead, we explain these properties from the perspective of identifiability. We derive two main corollaries from our identifiability result. Corollary 4.1 states that concepts are encoded in the matrix A given the relationship between the function of x and the log probability of the concept given x. We can see that the difference in representations of two counterfactual pairs, differing only in one latent concept, is related to a specific column of A, scaled by a factor derived from the probabilities of the concepts. This corollary reveals that the weights learned through linear probing are closely tied to the linear transformation A from our identifiability results, with the important relationship that the weights multiplied by A equal the identity matrix. This previously unexplored relationship provides a unified framework for understanding the linear representation hypothesis across its various forms, including concepts as directions, concept manipulability, and linear probing. Specifically, concepts as directions and concept manipulability focus on extracting or manipulating columns of A, which correspond to the latent concepts. Linear probing, however, involves learning the rows of W, which map the learned representations to the concept space. By utilizing the relationship between W and A, we show that these different aspects of the linear representation hypothesis are interconnected through the same linear transformation A. This unified perspective highlights how A serves as the foundational structure linking concept representation, manipulation, and probing. Finally, we will present experiments conducted on both simulated and real data to further support our findings.